Swayam Prabha. Digital India. Educated India.
Good morning, everybody. Today we will discuss the remaining part of simple algorithm. You may recall that we derived till the discretized x momentum equation, and also we discussed discretized continuity equation and some other aspects of the solution algorithm. So today we will start with y momentum equation, and we can see y momentum equation here at the first place has been written in terms of weak conservative form, but then we change it to strong conservative form. That means with del x of uv we get 1 by re del 2v del x2. Also with del x of del y of v square we get 1 by re del 2v del y2. Del y is operating on both, so this is something similar to strong conservative form, and then we integrate it over v control volume. Now when we define v control volume, Vij velocity is defined at the center of the cell, and the neighbors are adjusted accordingly. Means defined, they're already defined, they're considered accordingly. Like this point is considered Pij, this point is considered as Pi j plus 1, and this point is Vi plus 1j, this point is Vi minus 1j, etc. And this control volume is V control volume, where Vij is defined at the center of the cell or center of the control volume. And we will perform the integration of this equation on this control volume. So we have written double integral dx dy. That is equation 8. Now we'll discuss, I'll go back again. Now integration of del v del t is very easy. So over the volume, delta x delta y by delta t into Vij at n plus 1th level minus Vij at nth level, del v del t. Now we will consider these two terms of integration. So double integral del x of uv minus 1 by re del v del x plus del y of v square minus 1 by re del v del y dx dy. This term we can consider as E2, and this term we can redefine as F2. Like x momentum equation, we define these bracketed terms which were derivative of del x and del y, E1 and F1 respectively. Here we are doing E2 and F2. Now performing the integration and applying Green's theorem, we can write this surface integral as the contour integral of minus F2 dx plus E2 dy. So E2 first will integrate, then minus F2 also will integrate, and this integration will be done. This is contour integral and will follow a cyclic integral. So you can see, like when we calculate E2 dy, we define E2 here. With dy we integrate, and then here it is f, again f2, E2 is defined again here, and but this time dy is in the negative direction. So you can see E2 I plus half j. So this is ij with respect to v. So this point will be I plus half j. So E2 I plus half j, which is defined here, into delta y minus E2 I minus half j into delta y. Since this is contour integral here and this is E2 dy, so on this side dy is positive, this side dy is negative. We are getting this. Next term is f2. f2 is defined here and here. So this is fi j plus half. Now fi j plus half into delta x, and delta x in the negative direction, that makes minus fi j plus half delta x, but f is having negative sign because of this integration through Green's theorem. So that then this negative and this negative sign makes it positive. So fi j plus half, f2 I j plus half, and here f2 I j minus half is defined here. So f2 I j minus half into positive delta x. So that makes this quantity positive, but it is having a negative sign, so that makes it negative. So f2 I j plus half minus f2 I j minus half into delta x. And that is how we evaluate this integral. So finally we can write delta x into delta y by delta t into Vij at the level n plus 1 minus Vij at the level n. Here E2 I plus half j into delta y minus E2 I minus half j into delta y plus f I plus I f2 I j plus half into delta x minus f2 I j minus half into delta x, and pressure is defined as pressure gradient is Pi j plus 1, which is defined here, minus Pi j, which is defined here. So Pi j plus 1 minus Pi j into delta x, and pressure is at the level of n plus 1. And we have already seen earlier, we did this substitution, what is the meaning of E2 and what is the meaning of F2. Now this equation 9, we have to now express in terms of u, v and their derivatives. So if we want to do that, we basically, we like here it is if E2 at I plus half location, and this is basically u into v. So how to find out at this location u into v? This is interpolation simply. Vij plus vi plus 1j by 2 will give v here, and uij j plus 1 by 2 will give u here. So we will look at the terms which are basically uij plus uij plus 1 by 2. That's what we said, uij plus 1 by 2 multiplied by vij plus vi plus 1j by 2. Vij plus vi plus 1j by 2. This 2 and 2, 4. This is 0.1 by 4, 0.25, and this quantity. Then we have 1 by Re del V del X. So this is 1 by Re V del V del X here is Vi plus 1j minus Vij by delta X. Vi plus 1j minus Vij by delta X. So similarly, this E2 quantity have to be the way we have done here, have to be found out here. So I'm not repeating that, it is straightforward. I'm going for calculation of F2 at the point ij plus half. So, and what is F2? F2 is V square minus 1 by Re del V del Y. So here V square has to be defined. That means this is Vij plus Vij plus 1 by 2 square. So let us see, Vij plus Vij plus 1 by 2 square. That means Vij plus Vij plus 1 square by 4, and this is 1 by 4, 0.25. And then again we have to see what is 1 by Re del V del Y here. 1 by Re del V del Y will be Vij plus 1 minus Vij divided by delta Y. So Vij plus 1 minus Vij by delta Y. Vij plus 1 minus Vij by delta Y, and Vij plus 1 minus Vij by delta Y. So this is how again it is straightforward to find out F2 at this point. That means F2 ij minus half we have found out. So all these quantities we find out the way we did for x momentum equation. Then what we have to do, these are nonlinear terms, quadratic terms, and these have to be linearized. So One part we write at nth level, another part we write at n plus 1th level. So exactly we did that for x momentum equation. So we can see here 0.25 uij plus uyj plus 1 we will write at nth level, and vij plus vi plus 1j will be at the level n plus 1. So these are the level n plus 1, these are the level n. Similarly, here also, this ui minus 1j plus ui minus 1j plus 1, this will be at the level n, and vi minus 1j plus vij will be at the level n plus 1. Exactly, we have done that. This is basically vij vi minus 1j, vij vi minus 1j at n plus 1, and ui minus 1j plus ui minus 1 j plus 1 at the level n. So this way we do the linearization, and then we substitute this in the original equation. That means these terms are substituted, which are basically discretization of E2 and F2. Pressure gradient term is already discretized, and temporal term is already discretized. So we write all these, and nonlinearity is removed through local linearization, and then we collect the terms. Just we are repeating the same procedure that we followed for x momentum equation. All the coefficients of vij at the level n plus 1. So these are the coefficients of vij, and the neighboring v's, that means vi plus 1j, vi minus 1j, vij plus 1, vij minus 1, those neighbors at the level n plus 1, those terms we have to identify, and their coefficients. A and B are respective coefficients of eastern neighbor, western neighbor, northern neighbor, and southern neighbors. Again, this term will be basically, if we follow what we did x momentum equation, delta x into delta y multiplied by vij at nth level divided by delta t. We did it earlier, delta x into delta y, vij at nth level, all three are multiplied divided by delta t. And this is the pressure gradient term. This is equation 10, which is found by integrating y momentum equation on v control value. We found x momentum equation integrating on x control volume, u control volume, and let us recapitulate. We found this equation 7 in our last lecture. We term by term explained, and much more detail than what we did today, because that was the introduction. So we derived equation 7. Now equation 7 and equation 10 are discretized x momentum equation and discretized y momentum equation, equation 7 and equation 10. Now if we want to evaluate equation 7 in implicit manner for 7 and 10 for all the v's, that means and all the u's. That means u I j, ui plus 1j, ui minus 1j, uij plus 1 and uij minus 1 at the level n plus 1, vij, vi plus 1j, vi minus 1j, vij plus 1, vij minus 1 at the level n plus 1, we'll get this equation. But in this equation, we'll see that pressure is also at the level n plus 1. Now, we have the basic field when we started the calculation for n plus 1, and that field corresponds to nth level. Nth level velocities are there, nth level pressures are there. So all those nth level velocities we have included in this coefficient terms. But nth level pressure is the only available pressure. We do not have pressure available at the level n plus 1. So these two equations in this form difficult to evaluate, because pressure at n plus 1, this level n plus, at the level n plus 1, pressures are not known. Basic velocities, that means velocities at nth level, pressures at nth level are all known. And we are implicitly calculating velocity at the level n plus 1, u velocity and v velocity. So that is what we have written here. Since the pressure at n plus 1th level not available, so we are, when we evaluate this equation, we approximate. And what is the approximation? We write pressure at nth level. If we write pressure at nth level, then we can do the calculation, but these u and v velocities will not be exactly n plus 1th level. They will advance towards a level which is n plus 1, but since correct pressure is not there at the level n plus 1, and we are just advancing them with the help of this equation, we are unable at this stage to satisfy continuity also. So these advancement of velocities are provisional advancement. So making use of the approximate velocity solution u star, a pressure correction delta P will evolve, which will give finally, so we are, that is why we are determining, evaluating uij, vij and all neighboring u's and neighboring v's, but we are not calling these values are n plus 1th level values. We are calling them as star values. So making use of appropriate velocity solution u star, this is u vector star, that means uv, both are meant, both are addressed by this. A pressure correction delta P will evolve, which will give Pn plus 1 equal to Pn plus delta P. So if we can evolve delta P, we can know somehow how delta P will be added to P to make it pressures at n plus 1th level, then these u stars will also be corrected as u n plus 1th level. As such, what we are writing is a pressure correction delta P will evolve, which will give Pn plus 1 equal to Pn plus delta P, and also a velocity correction UC, which will be obtainable. As such, UC will correct U star in such a manner that U n plus 1, this is vector U, means U and V both are covered, U star plus UC, and then we'll get Un plus 1. So, and we'll get Pn plus 1 also. That is why equation 11 and 12 are making a projection for velocities at n plus 1th level. And then these two equations required to be corrected. When the pressure will be corrected, U star will also be corrected to U n plus 1. Now, that is why equation 11 and 12, if we look at it, and if we look carefully equation 7 and 10, let us compare equation 7 and 11. Both are x momentum equation. Equation 7, everywhere we have written uij and their neighbors ui plus 1j, ui minus 1j, uij plus 1, uij minus 1 at the level n plus 1. And pressures are written at n plus 1. Whereas equation 11, this is also x momentum equation, but all the velocities uij, ui plus 1j, ui minus 1j, uij plus 1, uij minus 1 are starred quantity. That means these are not exactly at the level n plus 1, somewhat similar to that, but different. That is why those are start quantities, and pressure is at nth level pressure. And if we subtract equation 11 from equation 7, everywhere with uij, ui plus 1j, ui minus 1j, we will get difference between level n plus 1 and star. That means that will be yet another equation with uij, ui plus 1j, ui minus 1j, uij plus 1, uij minus 1, but C, instead of star, we'll write C on them. Those are correction terms associated with corresponding starred terms to make these starred terms n plus 1. And pressure will also be corrected by delta P at each pressure point, so that P ij, pi plus 1j, pi minus 1j, all these, instead of being defined at the level n, after adding delta P, they will be at the level of n plus 1. So, if we subtract equation 11 from equation 7, we'll get this equation. Instead of u n ij n plus 1, we are writing uij c, velocity correction. And exactly with uij n plus 1, the coefficients which were there, those coefficients are there. Similarly, the neighboring velocities ui plus 1j, ui minus 1j, uij plus 1, uij minus 1, these are not at the level n plus 1, but we are writing, or we are defining them as with a superscript c. So these are again the velocity corrections of the velocities at those specified points. And everywhere, at every point, p at the level n plus 1 and p at the level n, those are, differences are basically delta p, because p at nth level, if delta p is added, will be p at the level n plus 1. Same philosophy applies for y momentum equation, and this we get if we subtract equation 12 from equation 10. We will get equation 14. This is velocity correction equation, or v velocity correction equation, and the pressure term, it is having delta p I j plus 1 minus delta p ij into delta x. Now from these two equations, again these two equations are basically implicit equations. Here uij correction, ui plus 1j correction, ui minus 1j correction, uij plus 1 correction, uij minus 1 correction, all are unknown. But delta p, if this is also unknown. So we have to break this implicitness through some approximation. And what we are doing, we are saying that these correction terms at the neighboring cells, correction terms, v velocity also, corrections at the neighboring points may be ignored. If we ignore them, we definitely, mathematically, we will not get exact expression. Expression will be different. But if we keep on doing iteration, we'll be able to compensate that. So from equation 13, neglecting u and b into a and b, that means neighboring velocity corrections and their coefficients, we are getting an explicit expression for uijc, velocity correction term. Simply we are neglecting this and we are expressing uijc equal to this term right hand side divided by its coefficient on the left hand side. So, and we do some little algebra, algebraic, sort of rearrangement, and we get this expression E1 into delta y, delta p ij minus delta p I plus 1j divided by 1 plus E1 a ij u, that is the coefficient of uij correction, pressure and velocity correction, this coefficient. So, and what is this E1? This E1 is not to be confused with E1, E2. We used in the momentum equation. There E1 or E2, whatever we used, those were basically superscript. This E1 is subscript. It's just a defined quantity, doesn't have any deeper meaning the way it was having for x momentum and y momentum equation. Here it is simply, to write uijc, that means velocity correction, from this expression after neglecting this neighboring terms. What we get when you do algebraic rearrangement, this E subscript 1, E1 is delta t aiju divided by delta x delta y. aiju is this coefficient of the velocity correction term, and this coefficient is same when we wrote uijn, and that when we derived u momentum equation, we had term by term expansion of aiju. Can again look at that. So everything is known. This is E subscript 1, E1, and from equation 14 then we can write Vij, velocity correction, or V velocity correction, and here we get this expression. Here also, just after obtaining the expression from this equation, neglecting the neighboring terms, whatever we get, if we reorganize algebraically everything, we will get this E2 appearing in numerator and denominator, and E2 is delta t aijv, this coefficient of Vij, whether at n plus 1 level or n level, that we derive that coefficient of Vij divided by delta x by delta y. So we have found out V velocity correction and U velocity correction. Now this U velocity correction and V velocity correction, if we add with the U star and V star, which we have provisionally calculated, we have provisionally calculated start quantities using nth level pressure, because only that pressure was available. N plus 1th level pressure was not available. So we have found out the start quantity. Now in the start quantity, if we add the correction terms, we are likely to get velocities at the level n plus 1. So we, in the original continuity equation, which was equation 5, previous lecture, we derived discretized equation 5. There uijn plus 1 and vijn plus 1 are substituted through this starred and correction quantities. Similarly, ui minus 1j at n plus 1 will be substituted. Similarly, vij minus 1 at the level n plus 1 will be substituted by corresponding starred and correction terms. Then from there we can get equation 17, which is an equation for pressure correction. You can see delta Pij with some coefficient will be delta P at the neighboring points. That means delta P at I plus 1j, delta P at I minus 1j, delta P at ij plus 1, j minus 1, and their coefficient together. and BP. This BP, if you do this substitution by yourself and try to write down the equation in resulting equation in this form, you will be able to write, and you will get one term BP, which is given by, as you can see, U star ij minus U star I minus 1j into delta y minus V star ij minus V star I j minus 1 delta x, as if this is basically the continuity equation written using start quantities. And if it produces 0, BP will be 0. That means that time when it will produce 0, if all start quantities have been elevated to n plus 1 level quantities. So after having, this is the meaning of BP. So effectively equation 17 is a Poisson's equation for pressure correction. So this is del square delta P equal to 1 by T, and we can clearly get divergence of velocity vector. This is U vector U star, means this U is small u, small v both. So basically this divergence of U star is del x of U plus del y of v. Both are start quantities, approximated quantity, and we can write their differences divided by delta x, differences divided by delta y. Now this will keep on changing. How? Because we will find out solving this delta p. This delta p will feed here. We'll find out velocity correction. We'll find out u velocity correction. We'll find out v velocity correction. We'll change this uijn plus 1 through velocity correction, vijn plus 1 through velocity correction. Again, use that value here. That will be new quantities, has not reached maybe in one go n plus 1. Still we'll use star, and then when it will reach really n plus 1 level, then this divergence quantity will be 0, and there will be no delta p correction, and whatever velocity correction we got the earlier iteration, that is the final velocity correction, and that means velocities at the level n plus 1 have emerged. We have got those velocities. So here is the systematic way of writing the algorithm. U star are obtained from equation 11 and 12. Let us go to equation 11 and 12. That means if we use pressure which we have gotten through the previous level of calculation, nth level of calculation, if we use them, we'll be only getting U star and V star. So this is U star are obtained from equation 11 and 12. Delta P is obtained equation 18. So using those U stars, if we try to get delta P, as you can see here, it will be a pentadiagonal matrix. It will not be known at ij, I plus 1j, I minus 1j, ij plus 1, ij minus 1. You have to run in the entire domain I equal to 2 to I max minus 1, j equal to 2 to j max minus 1, and you will get this matrix. Solve it, delta P will be obtained, and then pressure corrections are obtained from equation 15 and 16. So as and when delta P is obtained, we can go back, we can look at equation 15, U velocity correction, equation 16, V velocity correction is obtained. Then they will update the velocity quantities, and P nu is obtained as Pn plus alpha into delta P, where alpha is relaxation parameter. Usually this is under relaxed. We'll have this discussion later. So pressure is updated, P at nth level with this delta P pressure correction. It is added with Pn and P nu emerges. So similarly, you also update Uij, Vij. So Uij nu is U star plus Uij correction, Vij nu is V star plus Vij correction, and P nu is Pn plus alpha delta P. So this way, you see, we are advancing from one level to another level. Treat the corrected pressure P nu as the new initial pressure Pn. Use Uij nu and Vij nu, which we have just updated, as Uijn and Vijn. Again calculate U star from 11 and 12. Repeat the steps 1 to 5 until a converged solution is obtained. And when you get converged solution you get when Bp equal to 0. That means effectively Bp is this term. This is basically, that means divergence of V at every cell will be 0. There will be no longer pressure correction. So Bp equal to 0. And this is how you get the velocity at n plus 1th level, or it will not change anymore if you reach a steady state. This is basic simple algorithm. Professor Patankar revised it in 1980 and gave a name simple R. While pronouncing, it pronounces simpler, but its actual meaning is simple revised. And simple revised, what is basically little quicker convergence. What is done? You go for equation 11 and 12. You remove the pressure terms, try to evaluate instead of U star through implicit calculation a quantity given by U hat. So you can see that U hat is computed from equation 11 and 12 with the pressure terms deleted from the right hand sides. Equation 17 then becomes a Poisson equation. That means equation 17 becomes a Poisson equation for pressure, not pressure correction. Equation for Pn plus 1, because now you bring in Pn plus 1, you did not use P at when you evaluated equation 11 and 12. This is Pn plus 1 rather than delta P, with U hat replacing U star terms in Bp. the Pn plus 1 obtained from these two steps replaces Pn in equation 11. So this way, equation 11, you drop P terms, you evaluate U star. Now this U star, there is no P, you are calling it U hat. This U hat, you are feeding these U's in equation 17, and you are solving not for or 18, you can say, really not 17. I mean, effectively it is equation 18, and when you get the final solution, that is basically not, you are not solving for delta P, but P at n plus 1th level. So you replaces Pn in equation 11 and 12, which are solved for, equation 17 then becomes Poisson equation for Pn plus 1 rather than delta P, with U hat replacing the U star terms in Bp. The Pn plus 1 obtained from these two steps replaces Pn in equation 11 and 12. So then this replaces Pn. Now we rewrite equation 11 and 12. Whatever P we get from the Poisson's equation for pressure, not for pressure correction. Now it becomes Poisson's equation for pressure. And then we use 11 and 12 and find out U star. This U star, with this U star, we again come back to equation 17, that, and we keep on calculating delta P 17 or 18, but we don't change the pressure because already we have finalized the pressure as Pn plus 1. But whatever delta P we get, we make use of that to get velocity correction, and we keep on updating velocity till we get the convergence. That means divergence of velocity in each cell is 0, and there is no longer delta P from equation 17. This is called simple revised, simpler. There is yet another modification which is called simple C. It was developed by Van Dormel and Raithby. I am not discussing this in this lecture because this is again, modification of the procedure to have little better convergence or little more accelerated calculation. If we have understood basic simple algorithm, then these modifications like simple revised or simple C are easy, absolutely no problem. Now we will, since in this calculation everywhere we will be getting equations in this form, whether it is 11 or 12 or 17, in this form, phi P, phi may be U, phi may be V, phi may be pressure, our variable of interest, and P is point Uij. So phi P, that means Uij or Vij or Pij with its coefficient. This is eastern neighbor, that means Ui plus 1j and its coefficient. Western neighbor Ui minus 1j and its coefficient. Northern neighbor Uij plus 1 and its coefficient. Southern neighbor Uij minus 1 and its coefficient. plus b. Same is the style of expressing, V momentum equation, pressure equation. Always we get in terms of, neighboring values, neighboring variables, and their coefficients. The current value of in the dependent variables, that is what is we are saying phi is, it may be u, it may be v, it may be p, are to be evaluated from the known values of coefficients. The evaluation algorithm will be same for the momentum equations and the pressure correction equation. On a rectangular grid, the dependent variables at one point, ij point, which is point P, may be expressed in terms of its neighbors. Again, whatever I have narrated, I have written it again. Instead of phi P, if we write uij, coefficient is aij. Instead of phi E, if I write eastern neighbor, ui plus 1j, coefficient is bij. Western neighbor, phi w, ui minus 1j, its coefficient, ui j plus 1, its coefficient, ui j minus 1, its coefficient, plus fij, all the remaining terms, where bij is equivalent to a Cij here. Bij is equivalent to coefficient of eastern neighbor AE, Cij is coefficient of western neighbor, Dij is coefficient of northern neighbor, Eij is coefficient of southern neighbor, and Fij to the free term B. The evaluation of U can be accomplished in the following ways. Because it is, again, if we can, it's not a tridiagonal matrix, but if we can solve in the format of tridiagonal matrix, we get some advantages. Vertical sweep upwards may be written in a pseudo Fortran code or pseudo C code also, you can say. Do 10, j varies from 2 to m minus 1. M is the maximum number of points. 1 to m. So 2 to m minus 1 we will run the loop. Similarly, in the other direction, it is 1 to L. So we will run 2 to L minus 1. So this do loop, j equal to 2 to m minus 1, I equal to 2 to L minus 1, and this is the algorithm. Aij, uij equal to bij, ui plus 1j plus cij into ui minus 1j. So this is, these are implicitly related. These will be evaluated by varying I equal to 2 to L minus 1, j equal to 2 to m minus 1, will get a system of algebraic equation. Whereas when we are setting this loop, that this barred quantities, u bar is the currently available value in storage, and all coefficients including fij are known. So we'll assume j plus 1, j minus 1, fij, these are known. We are varying in I. So for each j, we shall get a system of equation if we substitute I equal to 2 to L minus 1. In other words, for each j, a tridiagonal matrix is available which can be solved for all I row of points at that j. Once one complete row is evaluated, then we go for next j. And at every j, we will see that j plus 1 and j minus 1 will be needed. And those values are which are available. Latest value we will club them together as known values, and they will be contributing as from their known quantities. So this is the vertical sweep, and earlier one, this is the horizontal sweep. Here you can see we have set the do loop, do 20 I equal to 2 to L minus 1, do 20 J equal to 2 to M minus 1, and now J plus 1, see earlier we bracketed these J plus 1, J minus 1 terms, and they were all given bar. These bar quantities are value in store. So we are, through algebraic equation, we are updating these quantities I plus 1, I minus 1 at a given J. Now, next, what at this stage what we'll do, these barred quantities are now I plus 1, I minus 1, and equation is implicit in J direction. Ij, J plus 1, J minus 1, these are not known. Again, U bar is currently available value in storage from previous calculations. For each I, we get a system of equation if we substitute J equal to 2 to M minus 1. So this is basically, J plus 1, J minus 1, for every J value 2, 3, 4, 5 up to M minus 1, we get a system of equations. A tridiagonal matrix is available for each I location. Once one complete column of points are evaluated for any particular I, means all J's, then next I will be taken up, and so on. The vertical sweep upward and downward are repeated. We will not only go from 2 to L minus 1, we will come from the topmost value to the bottommost value also. We'll just reverse the sweep. Vertical sweep upward and downward are repeated. Similarly, horizontal sweep forward and rearward, this can also be repeated until convergence is achieved. For solving tridiagonal system, the tridiagonal matrix algorithm TDMA due to Thomas, which we have already used it, Thomas algorithm is deployed. So this is called line by line TDMA. This is quite similar to alternating direction implicit scheme, but here we are just from the field variables, we are updating the values, keeping basically one variable direction implicit. Once we are keeping J variables implicit, and for every I we are running basically tridiagonal matrix in J direction. Another sweep, we are keeping J direction fixed. That means at given J, we are forming TDMA in I direction, I equal to beginning to end point, and evaluating. So this is, even if the number of unknowns are not 3, Ij, I plus 1j, I minus 1j, Ij plus 1, Ij minus 1. These are unknown, implicitly related, but through line by line TDMA, we can again evaluate such matrix without going into a different type of matrix solver, using similar process what we did for solving tridiagonal matrix TDMA. So this is called line by line TDMA. Now these are some useful references. As you can see, first one is a published paper by Professor Patankar. Second one is Professor Patankar's book. Third one is the first paper on solving full Navier-Stokes equations, on solution of full Navier-Stokes equations, as I mentioned, by Patankar and Spalding. And the fourth one is a textbook, volume 2 of Computational Techniques and for Fluid Dynamics by Professor Fletcher. And fifth one is also another book by Professor Roger Pire and Ted Taylor. This is a Springer book, very good book. So whatever I have explained, you will get the same material in different way of writing through different explanations in these papers and books. Thank you very much. Thank you.